In 2021, Google built a crystal that ticks forever without a single joule of energy, and it broke physics. By the end of this video, you'll understand exactly how time crystals violate a rule we thought was unbreakable, why scientists spent 4 years proving they were impossible before someone built one anyway, and how this forbidden matter could finally make quantum computers actually work. Let's start with something you already know. Every machine, every clock, every beating heart, they all need energy to keep moving. This isn't just an observation. It's a law. The second law of thermodynamics says that any system doing work must consume energy. Period. Except, what if it didn't? In 2012, Nobel laureate Frank Wilczek at MIT was thinking about crystals. Normal crystals, like salt, like diamonds, they're atoms locked into repeating patterns in space. They break what physicists call spatial symmetry. Instead of atoms being anywhere, they're stuck in a grid. Wilczek asked a strange question. What if a crystal could break symmetry in time instead of space? Imagine atoms that don't just sit in a pattern. They dance in a pattern. Forever. Not because something's pushing them, but because that's their lowest energy state. Their ground state. They're already as relaxed as they can possibly be, and they're still moving. This should be impossible. Motion requires energy. That's not philosophy. That's thermodynamics. Wilczek published his idea in physical review letters anyway. And then the physics community did what it does best. In 2015, physicists Haruki Watanabe and Masaki Oshikawa published a mathematical proof. Not an argument, a proof. They showed that Wilczek's continuous time crystal was thermodynamically forbidden. A system in equilibrium cannot spontaneously oscillate. The dream was dead. Except, physicists are stubborn. See, Watanabe and Oshikawa proved that continuous time crystals, ones that tick on their own in perfect equilibrium, were impossible. But what about systems that aren't in equilibrium? What about systems you kick periodically? Imagine pushing a child on a swing once every second. You'd expect them to swing once per second, right? Matching your pushes. That's normal physics. But what if the child swung once every 2 seconds instead? You push twice, they swing once. Not because of friction or weight, but because the system itself refuses to sync up. That's a discrete time crystal. That's the loophole. In 2016, 2 teams raced to build the first one. At UC Berkeley, Norman Yao's group used nitrogen vacancy centers in diamonds, tiny defects in the crystal structure that trap electrons. At the University of Maryland, Christopher Monroe's team used 10 ytterbium ions suspended in electromagnetic traps. Both teams hit their systems with laser pulses at precise intervals. Both observed the same impossible thing. The systems oscillated at exactly half the frequency they were driven at. Push it at 100 megahertz, it responds at 50. Every time, with machine precision. This wasn't random fluctuation, it was stable, repeatable, and it shouldn't exist. Nature published both results in March 2017. The impossible had arrived. But here's where it gets really interesting. In November 2021, Google's quantum team used their Sycamore processor, the same one that claimed quantum supremacy in 2019, and built a time crystal from 20 superconducting qubits. 20 quantum bits, oscillating in lockstep at half the driving frequency, refusing to heat up despite constant energy injection. Normally, when you pump energy into a quantum system, it heats up, the delicate quantum states collapse. Information scrambles into thermal noise. This is called decoherence, and it's the single biggest obstacle to building useful quantum computers. Qubits in today's machines lose their quantum properties in microseconds, sometimes nanoseconds. But time crystals don't heat up. They use a phenomenon called many-body localization to stay protected. Instead of spreading energy throughout the system like water soaking into a sponge, the energy stays locked in local patterns. The quantum information survives. This isn't just weird physics. This is potentially the solution to quantum computing's biggest problem. In 2024, researchers at Tech in the Netherlands demonstrated that time crystalline order could extend coherence times in quantum systems. Not by building better refrigerators or better isolation chambers, but by exploiting this strange phase of matter that refuses to thermalize. Imagine quantum computers where the most fragile operations happen inside time crystals, protected bubbles where decoherence can't reach, where quantum information keeps ticking perfectly, indefinitely. We're not there yet, but the path exists now, and it gets stranger. In 2022, researchers created a time crystal in superfluid helium, 3 using magnons, quantum particles of magnetic oscillation. This system showed time crystalline behavior that could theoretically last forever. Not microseconds, not minutes, indefinitely. We've now created time crystals in at least 5 different physical platforms: trapped ions, superconducting qubits, diamond defects, nuclear spins, and magnons and superfluids. So let's zoom out. Were time crystals really? They're the first known non-equilibrium phase of matter. Substances with properties that are literally impossible when a system is at rest. They prove that the universe has more states, more possibilities, than classical thermodynamics ever predicted. Their motion without energy consumption, order that emerges from being driven, not despite it. Frank Wilczek proposed something impossible in 2012. Scientists proved it impossible in 2015. And then other scientists found a loophole and built it anyway in 2016. That's not failure. That's physics. Quantum computers today are like vacuum tubes before the transistor. Fragile, huge, unreliable. Time crystals could be the breakthrough that makes them practical. Not by engineering around decoherence, but by finding a phase of matter where decoherence doesn't apply. If this video made time crystals click for you, subscribe. Next week, we're covering something equally impossible: negative temperature. Yes, temperatures below absolute zero exist, and they're hotter than anything in the universe. I'll explain why that sentence actually makes sense. End card, subscribe button animation, next video thumbnail preview.